and I would like to tell you about the paper on the automorphism group of a binary form associated with algebraic trigonometric quantities that will soon appear in the Journal of Number Theory. So let's take a binary form f with integer coefficients degree d at least 3 and non-zero discriminant d. We can ask how many integers are being represented by this form, and so we define the quantity r sub f of z, which counts how many integers m of absolute value at most z are there that are represented by f. And in 2019, Stewart and Zhao proved that there exists a positive number c sub f such that r sub f of z is asymptotic to c sub f times z to the power of 2 over d. And so as a consequence of this, they also proved that the asymptotic density of integers represented by such binary forms is 0. Further, they showed that this quantity c sub f is a product of two quantities, w sub f and a sub f, where a sub f is the area of the fundamental region of f, and w sub f is a rational number that can be derived from the rational automorphism group of f. And in this paper, we aim to compute the automorphism group and the associated quantity w for the following four families of binary forms: Chebyshev binary forms of the first kind, Chebyshev binary forms of the second kind, homogenizations of the minimal polynomial of twice the cos of 2 pi over n, and a homogenization of the minimal polynomial of twice the sine 2 pi over n. So the automorphism group can be defined as follows. If we take a 2 by 2 matrix with rational coefficients, we can define a new binary form f sub a in the following way. So we are acting on f by a, and the rational automorphism group of f is a collection of all matrices that fix f under this action. It turns out that the automorphism group is a finite subgroup of GL2Q, provided that the degree is at least 3 and the discriminant is not 0. And further, we actually know exactly what finite subgroups of GL2Q look like. They belong to one of the 10 equivalence classes under that you can see on the screen under GL2Q conjugation. So based on this fact, Stewart and Zhao actually derived a formula for W sub f. This is a table that was taken from their paper. And here you can see numbers m1, m2, m3, m4, and m appearing. These numbers are related to certain sublattices of Z2 that are associated with the automorphism group. But with the exception of the automorphism group of the fourth Chebyshev binary form of the second kind, in our case, these automorphism groups will actually be subgroups of GL2Z. And so as a consequence of this, all of the quantities m1 up to m4 and m and 1 will be equal to 1. And so W sub f will have a very simple formula. In particular, it will equal the inverse of the size of the automorphism group itself. So the quantities W sub f were computed in some special cases. So Stewart and Zhao derived them for binomial forms of degree at least 3. And Fouvrier and Waldschmidt derived them for cyclotomic binary forms. And now here's a statement of our first result, theorem 1.1, where we find the automorphism group of the homogenization of the minimal polynomial of twice the cos of 2 pi over n. So here the cases 1, 2, and 3 should be viewed as basically standard. And non-standard cases are all listed in part 4. So here they are, all listed in this table. There are 7 special binary forms whose automorphism groups are interesting enough. And so we can find an associated quantity W as well. And of course, we establish an analogous result for the minimal polynomial of twice the cos, twice the sine of 2 pi over n. We find the automorphism group of such binary forms as well as the associated quantity W. So here's the statement of theorem 1.3, where we find automorphism groups of Chebyshev binary forms. The most interesting case, as I would mention before, is the case of the automorphism group UN when n is equal to 4. In this situation, our automorphism group actually, some matrices in our automorphism groups actually have non-integer coefficients. Okay, so in terms of so we of course we find the associated quantity W as well, and for the ideas of the proof, we so in the case of the homogenization of the minimum polynomial twice the cos of 2 pi over n, we simply look at the factorization of psi sub n. We notice that when n is odd, then psi sub n and psi of 2 times n are related. And we notice that if 4 divides n, then psi sub n can be expressed as g of x squared y squared for some other binary form g with integer coefficients. And so it's sufficient to analyze two cases, when n is odd and when 4 divides n. If n is odd, we make use of the fact that twice the cos of 2 pi over n and twice the cos of 4 pi over n are algebraic conjugates. I can derive some useful information from that. And if 4 divides n, then we make use of the fact that this group that you see on the screen, it's isomorphic to D2, and this group has to be contained inside the automorphism group of C sub n. And then we prove that the set equality does not hold if and only if n is equal to 24. Now for the proof of theorem 1.3 about the automorphism groups of Chebyshev binary forms, instead of looking at T sub n and U sub n, we look at their associated binary forms U sub n, tilde U sub n, and tilde V sub n. These are well known in the literature, and both of these are actually monic in the sense that the coefficient of x to the n is going to be x to the degree will be equal to 1. And so we will notice this these interesting factorizations, and then we prove that if one of the factors for these binary forms, the C sub n factor, is greater or equal to 5, then we can say something meaningful about the automorphism group of U tilde sub n or V tilde sub n. And so at this point, it remains to consider all the special cases. There's only 13 of them, and it turns out that among them, there's only one that kind of stands out, and it's tilde U sub 5 of n, not 4, but 5. Okay, and that's it. Thank you very much for your attention. I hope that you'll enjoy the article.